On the night of February 24th, 2026, a telescope in the Chilean Andes did something that had never been done before in the entire history of astronomy. It photographed a patch of sky, compared every pixel to images taken weeks earlier, identified everything that had changed, every object that had brightened, dimmed, appeared, or disappeared, and sent out 800,000 individual alerts to astronomers around the world in a single night. By the time the sun rose over Chile the following morning, the global astronomy community was overwhelmed. Email systems at research institutions were flooded. The servers hosting the alert distribution network were running at maximum capacity. Scientists at universities from Tokyo to Toronto to Cape Town were opening alerts, classifying events, and scrambling to redirect other telescopes toward the most scientifically urgent. Detections. Stephen Smart of the University of Oxford, serving as scientific lead for one of the 7 data brokers processing Rubin's output, described it simply: everything that changed, appeared, or disappeared was cataloged and triggered an alert. 800,000 things changed in the sky in one night. Rubin found all of them, and the Internet of professional astronomy, the networks, the servers, the communication channels between observatories worldwide, was not ready for the scale of what had just arrived. The Vera C. Rubin Observatory was not supposed to break anything. It was supposed to change everything, gradually, systematically, over a decade of continuous sky survey. But the moment its real-time alert system went live on February 24th, 2026, the scale of what this instrument could do became viscerally real to a scientific community that had been anticipating it for years. The observatory sits at 2,682 meters elevation on Cerro Pachón in northern Chile, and its primary scientific instrument is the LSST camera, the legacy survey of space and time camera, the largest digital camera ever built. It weighs approximately 3,000 kilograms, roughly as much as a small car. Its sensor array contains 189 individual charge-coupled devices arranged in a mosaic. Its total resolution is 3,200 megapixels. And to display a single one of its full-resolution images at actual size would require hundreds of ultra-high-definition television screens arranged side by side. Every 40 seconds, this camera takes a complete exposure covering a patch of sky equal to 45 full moons. Then the telescope moves to the next patch, then the next. Over the course of a night, it covers the entire visible southern sky. And every time it images a region it has photographed before, the observatory's computing pipeline compares the new image to the old one, pixel by pixel, looking for differences. Differences are discoveries. And on February 24th, there were 800,000 of them. Those 800,000 alerts drew astronomers' attention to new asteroids, exploding stars known as supernovae, active galactic nuclei, the glowing supermassive black holes at the centers of galaxies, and variable stars whose brightnesses change over time. Each alert contained not just the detection, but a preliminary classification, a set of coordinates, a light curve showing how the object's brightness had changed over time, and links to the archival images that anchored the comparison. The 7 data brokers, receiving Rubin's alert stream, software systems developed by teams at institutions worldwide specifically to handle this volume of data, immediately began sorting, filtering, and routing the alerts to subscribing scientists based on their research interests. A team studying supernovae received alerts flagged as supernova candidates. A team studying near-Earth asteroids received alerts flagged as fast-moving solar system objects. A team studying active black holes received alerts flagged as active galactic nuclei with unusual variability. The system worked as designed. It was simply larger, faster, and more comprehensive than anything the community had previously experienced. The observatory is expected to eventually reach 7 million alerts per night. 7 million. On its first real operational night, Rubin produced 800,000. The full capacity is nearly 9 times that. The global astronomy community has approximately 10 years to figure out how to process what is coming. The asteroid that broke the internet in a different way had actually been found months earlier, during Rubin's commissioning phase in May 2025. Designated 2025 MN45, it was one of approximately 1,800 asteroids detected during the First Look program, a test run of Rubin's solar system detection capability that used repeated imaging of the Virgo cluster region from April to May 2025. Most of those 1,800 asteroids were unremarkable in isolation, though their sheer number, found in a handful of nights of commissioning data, demonstrated that Rubin would rapidly expand the catalog of known solar system objects by millions over the course of its survey. But 2025 MN45 was different. Scientists spotted asteroids that spin faster, but they tend to be much smaller, between 10 and a few hundred meters. For asteroids the size of 2025 MN45, about 700 meters across on average, we didn't expect we would find something spinning faster than 10 minutes, said Dmitry Vavilov of the University of Washington, a co-author on the discovery paper. 2025. MN45 completes a full rotation every 1.88 minutes. At that spin rate, a loosely bound pile of rubble held together only by gravity, which is what most asteroids of this size are, believed to be, would fly apart. The centrifugal force at the surface would exceed the gravitational force holding the particles together. The fact that 2025 MN45 has not flown apart means it must be structurally coherent, a single solid object, not a rubble pile. It might be a fragmented chunk of a long-dead planetary core from the early solar system, broken in a collision and left to spin wildly through space for the last 4.5 billion years, said Greenstreet, the paper's lead author. A piece of a dead planet's core, spinning at 32 times the speed of any asteroid of comparable size that science had ever found. Found in the first weeks of Rubin's test observations, the record-breaking asteroid was the first peer-reviewed scientific paper ever published using Rubin data. The announcement on January 7, 2026, generated the kind of immediate public attention that science rarely produces. The combination of a 700-meter rock spinning fast enough to tear itself apart if it were any less solid, the implications for planetary defense, and the fact that Rubin had found it in its first few nights of operation. The study provided crucial information about asteroid composition and evolution, and demonstrated how Rubin is pushing the boundaries of what we can discover within our own solar system. Within days of the announcement, the paper had been downloaded hundreds of thousands of times. The search term Rubin Observatory asteroid trended on multiple platforms simultaneously. Scientists who had spent decades advocating for Rubin's construction pointed to 2025 MN45 as proof that the observatory was already delivering science beyond what had been anticipated. But the discovery that most directly connects to the biggest questions in all of cosmology came not from asteroids or supernovae alerts, but from a different Rubin data product entirely. Rubin's Quantum Magazine profile from May 2026 revealed that the observatory was already tracking failed supernovae, events where massive stars collapse directly into black holes without producing the brilliant explosion that would normally signal their death. Failed supernovae are extraordinarily difficult to detect. A star simply disappears. There is no bright flash, no expanding shell of glowing gas, no neutron star remnant emitting radio waves. From Earth's perspective, a failed supernova looks exactly like a star that was there last week and is not there this week. No previous sky survey had the cadence and the rate of repeat imaging to reliably catch stars disappearing on timescales of days to weeks across large areas of sky. Rubin returns to every part of the sky every 3 to 4 nights. That cadence is precisely what is needed to catch a massive star vanishing between visits. The implications are significant. The rate at which massive stars collapse directly into black holes, rather than exploding as supernovae, affects the chemical enrichment of galaxies, because a successful supernova disperses the heavy elements fused in the star's interior into the surrounding gas, while a failed supernova locks them inside the black hole. If failed supernovae are more common than models assume, the chemical evolution of galaxies across cosmic time is different from what simulations predict. The interstellar visitor connection completes the picture of what Rubin has already demonstrated about its capabilities. With the Vera C Rubin Observatory now scanning the sky, interstellar objects like 3I Atlas may soon become routine discoveries. The detection of 3I Atlas in July 2025 required a network of smaller survey telescopes operating over weeks to confirm the object's hyperbolic trajectory. Rubin, with its combination of sky coverage, cadence, and depth, would have detected 3I Atlas earlier, tracked it more continuously, and provided higher quality photometric data from the moment of discovery. Simulations of what Rubin will detect over its 10-year survey, calibrated against the 3 confirmed interstellar objects found since 2017, predict between 1 and several interstellar objects per year once the full survey is operating. The Rubin era is the era in which interstellar visitors stop being once-in-a-generation events and become part of the regular observational catalog. The infrastructure for rapid response, the alert system, the data brokers, the global network of follow-up telescopes, that Rubin validated on February 24th with 800,000 alerts is the same infrastructure that will mobilize within hours when the next interstellar object is detected. The debut images released in June 2025 revealed more than 10 million galaxies in and around the Virgo cluster, many of them never studied before, as well as 2,000 previously undiscovered asteroids spotted after just a few nights of observations. 10 million galaxies, 2,000 asteroids, in a few nights of commissioning data from an observatory that had not yet begun its formal survey. By July 1st, 2026, when the legacy survey of space and time officially began, Rubin had already found more than 11,000 new asteroids, confirmed the fastest spinning large asteroid ever discovered, produced 800,000 alerts in a single operational night, and demonstrated that its pipeline for detecting failed supernovae and interstellar objects was functional. The formal survey will run for 10 years. The first few months of data have already produced results that previous observatories would have celebrated as career-defining discoveries. The observatory, named after the woman who proved that dark matter exists by watching galaxies rotate in ways that visible matter alone cannot explain, has already begun doing what she believed astronomy was for, looking at the universe not for what we expect to find, but for what the universe actually contains. The night sky over Chile has not changed. The same stars, the same galaxies, the same asteroids, the same transient events that have been happening across the cosmos for billions of years were all happening before Vera Rubin existed. What changed on February 24th, 2026 was not the sky. It was our ability to see it. 800,000 events in one night. 7 million eventually. 10 years of continuous watching. The greatest cosmic movie ever made, now filming. And the internet, the global network of scientists, institutions, servers, and communication channels that tries to keep up with what Vera Rubin is finding, is going to need to get faster. The Dark Energy Survey connection adds one more dimension to what Rubin is already changing. In January 2026, the Dark Energy Survey collaboration published its collected information on hundreds of millions of galaxies across the universe. The DES, which operated from 2013 to 2019 using a camera on a telescope at the same Chilean site where Rubin now operates, represented the most powerful dark energy survey of its era. Its final dataset, hundreds of millions of galaxies mapped across a significant fraction of the southern sky, took 6 years to collect and years more to analyze. Rubin will produce equivalent data volumes in weeks. It will accumulate DES scale datasets repeatedly, building up a temporal record that the DES could never generate. The weak gravitational lensing measurements that DES used to map dark matter will be possible with Rubin at 10 times the depth, 10 times the sky coverage, and with the added dimension of time. Because Rubin sees the same galaxies repeatedly, measuring how their apparent shapes change as dark matter structures grow and shift on cosmological timescales. The dark energy measurement that required a decade of DES operation is now a continuous, real-time output of an observatory that never stops watching. Every night that Rubin operates, IT adds to a dataset that is simultaneously the most comprehensive map of the present-day universe ever assembled and the most detailed time-lapse record of how the universe is changing. The internet broke on February 24th because 800,000 discoveries arrived in one night. In 10 years, the total will be measured in the billions, and every one of them is a piece of the answer to the question that defines modern cosmology: what is the universe actually made of, and where is it going?